Okay, so good morning, everyone. We are going to start our plenary session. I have the pleasure to chair it, to chair at least the first part of it, which is the awarding part. So I'm Nabila Aghanim from the EAS Council, and I'm in charge of the prize committee of EAS. And it's really a pleasure to start this session because we are going to honor our young colleagues who got awarded the MERAC Prize for the best PhD, 3 award for this time. They will be handed by Lucio, the representative of the MERAC Foundation, funding these prizes. So I'm speaking a little bit too long, just to allow for people to come in the room. Sorry about this long introduction. So I'll take also the opportunity to remind you that there is a poster contest and that you can, and you're very encouraged to vote for the best poster. There are prizes for the winners, so we encourage you to vote for yourselves as well, if you wish, but please vote for the posters. I guess we can start, maybe, Lucio, if you agree. And we will start with the first award.
So it's a pleasure to announce the first prize. The MERAC Prize 2024 in Theoretical Astrophysics is awarded to Lorenzo Gavassino for his thermodynamics-based formulation of relativistic viscous hydrodynamics for multi-messenger and gravitational astronomy. Congratulations.
So congratulations to you, Lorenzo. And we are going to listen to your presentation about embedding irreversibility in general relativity. Thank you very much in advance.
Thank you. Thank you very much. It's a great honor for me to receive the MERAC Prize. I feel a little bit under pressure because I feel that I need to justify to you why I won such a huge prize, which is a titanic task indeed. But I've decided that I will just try to give you an overview of what I do, what's the main topic, and what the big open questions are in my field. So I would like to start with a little experiment. How many of you have read a book about relativistic thermodynamics? Please raise your hand. Well, not so many. Well, indeed, I would say that for the time being, an actual book on relativistic thermodynamics does not exist. In the sense that relativistic thermodynamics is the theory that tells you how the principles of thermodynamics must be adapted in the context of general relativity. And it's quite strange that relativistic thermodynamics acquired a bad reputation for historical reasons. But think about it. I mean, thermodynamics is all about two things. Energy, through the first law of thermodynamics, you know, heat, work, and so on, and entropy, which is basically time. It's what gives an asymmetry between past and future, right? Relativity changes all of this. So is it possible that we couldn't find something interesting to say about what happens to thermodynamics when I go to a relativistic world? So the result of my PhD work, which now I will begin to move the slides, okay? In the end, I decided to do a little bit of introduction without slides. So now I will tell you that my PhD thesis, the main result, was the ability to discover that the theory of relativistic thermodynamics contains much more than the non-relativistic analog. It's a very rich theory, although nobody knows about it, but I hope that after today you will know it. So let me give you an example of an interesting result, something that is rather peculiar and that I discovered in my work and that I would like to share. So let's see if it works. OK, so in this picture, you see the mass-reduced diagram of neutron stars. It's not super up-to-date, 2017, but for our purposes, it's fine. So on the x-axis, you have the radii. On the y-axis, you have the masses. Now, I would like you to focus your attention on the upper left corner in green. You see an inequality there, which I've rewritten here on the right. Speed of sound smaller than the speed of light. Now, since I am a theoretical physicist, for me, the speed of light is 1. So from now on, I will write speed of sound smaller than 1. This is known as the causality criterion. It's the principle that you don't want sound to transport information faster than the speed of light. Now, it's well known, and it introduces a limit on the mass-radius relations, because if an equation of state wants to reach that region, that green region in masses and radii, its equation of state would need to transfer information faster than light. Now, I would like to show you now, I convince you with some little arguments and idea, that I can derive this inequality from thermodynamics alone without ever making any reference to the principle of causality, but just from stability. So to do that, a little bit of recap of special relativity, everybody knows. So what you hear is the usual discussion when you also talk about special relativity in general. Moving cars are shorter, ticking clocks are slower. Now, this is the easy part, okay? This is not the very interesting aspects of relativity. The most interesting aspect is a third phenomenon, which is known as relativity of simultaneity. It's the famous fact that if now I snap my fingers simultaneously, you see this happening simultaneously, but when someone comes here running, they will see the two snaps happening at a different time. This changes completely the mathematical structure of everything we know. It's the reason why there is no actual relativistic quantum mechanics, and rather there is quantum field theory, because this fact changes everything. And it's also the origin and the explanation for most of the paradoxes that we encounter in relativity. Everybody knows the twin paradox. Let me tell you about another fun paradox, the famous paradox. So if does this moving car fit into the parking? Okay, so on the left, you are in the reference frame of the parking. The car is shorter by length contraction, and it fits. But then in the other reference frame, it's the parking that is shorter, so the car does not fit. So is this a contradiction? Is this a paradox? Well, actually, the resolution is simple. There are two facts happening here. First fact, the front of the car is in the parking. Second fact, the back of the car is in the parking. In one reference frame, these two things happen at the same time. In another reference frame, they happen at a different time. And so there is actually no paradox. Everything is fine. Now, these are the easy thing. Now, let's talk about something. Oh, what happened? I don't manage to go ahead. Okay, it takes some time. Okay. And now we come, actually, if you want, to the main. This is the only thing I would like you to remember from this presentation. Okay, so let's imagine that for some reason, sound was traveling faster than the speed of light. So what you can see here is a Minkowski diagram. On the left, there is the perspective of some observer, A, Ellis. Usually, this is the definition, the term that we use in physics. Now, this is a Minkowski diagram. You see the sound wave that at the beginning is generated here. The mouse doesn't work great. Okay, so it's generated and then it travels faster than the speed of light. Now, suppose that there is a little bit of dissipation. So at the beginning, the sound wave is very intense, it's strong, but as it travels in space-time, it becomes smaller. And this is the purpose of the shades of red. At the beginning, red, it's stronger, and then it becomes smaller. But now, let's use relativity of simultaneity. If I take another observer, Bob, that moves very fast towards the right, okay, then from their perspective, all the structure of the sound wave is inverted. So at the beginning, you have the weak sound wave, and at the end, you have the strong sound wave. All the chronology of the process is backwards. What does it mean? That from the point of view of Ellis, the fluid wants to approach equilibrium. The fluid wants to relax, sound wants to disappear. From the point of view of Bob, the fluid is actually unstable. If you impress a little kick, this will grow, and the system will eventually, it's slowing. I'm trying to move ahead with the presentation. Okay. And from the perspective of Bob, the fluid actually explodes. And you actually see this with equations. When you do the calculation, you see these problems. Now, let me show you how to derive this simple idea from thermodynamics. Okay, there is some math in there. Okay, so I will try to skip all the math and just give you a little bit of idea. All my work is pen and paper, okay, but I will just try to give you a little bit of feeling of what happens. So we know from thermodynamics that there are some quantities that must be positive by construction, at least in matter. You can find it in textbooks. There are specific heats, some susceptibilities and things like that. And those usually come from the condition that you want, that when you put two pieces of matter in contact with each other, they want to remain homogeneous. You don't have a runaway situation where, for example, all the energy flows from one body to the other, okay, which is the reason why we have these coefficients. And these are obtained by maximizing the entropy of the couple of systems and see what is the state, and you want to require the entropy to be maximized in the homogeneous configuration. Now, you need to do it in relativity, so I tried to do it in relativity. It was a little fun experiment, and what I get is the following. You don't really need to follow the math. Just consider when I maximize the entropy, I have this matrix, and I want the matrix to be positive definite. And if I am in the rest frame, okay, nothing strange. I get the usual inequalities, specific heat positive, speed of sound positive, and all the rest, everything well known. But then when you do the calculation, and you need to set up some rigorous framework, which is half of the work of my thesis to do it, then what you get is basically the same metric with one small difference. There is a V of diagonal. Now, this is actually a V over C. So it's an effect that disappears when you remove relativity. So it's an intrinsic relativistic fact. When you impose positive definiteness, you obtain a different stability condition. The stability condition is the second. The speed of sound to the -2 must be bigger than the velocity. V is the velocity of the fluid. Now, if you require this to hold for every velocity, what you get, speed of sound smaller or equal than 1. Otherwise, fluids would explode. And now the interesting thing is that this is a very simple example of a more general idea, a more general theorem that I managed to prove from relativistic thermodynamics, which is something I call the stability causality theorem, which is, if you want, the most important result of my thesis, is the statement that stability and dissipation are Lorentz invariant features of a model if and only if information cannot travel faster than light according to such model. What does this mean? That for sure you know that if you have some equations and by mistake there is some tiny little information that goes faster than light, maybe you expect it to be small, you expect it to be rounding error, but if there is, there will be some observer who will see the thing explode. And why is this interesting? Well, because there has been a debate going on for 80 years about the existence of relativistic Navier-Stokes. This is kind of hard to believe it, okay? Relativity is 100 years old, so it's 80 years that we debate, does relativistic Navier-Stokes exist or not? And the reason is that when you write the equations for example, you want to work in general relativity, you want to model some fluids, here you have, for example, a neutron star merger or an accretion disk, you want to model it, you must include many effects, but let's say that you want to be simple, you just want to use Navier-Stokes because in the end, these are just fluids. So let's use Navier-Stokes. The equations that you find in books is this one. You can find it in Weinberg textbook, you can find it in Landau-Lifshitz, you can find it in the major textbooks on the topic, okay, on general relativity that have some section about this. And they will typically write this equation. We don't need to look very much at the detail, but there is the blue part that is the fluid without viscosity, and then the viscous correction. There are some metrics, things, calculations there. So when you actually solve these equations, what you get is indeed the same problem. which has caused debate for years, because when you solve relativistic Navier-Stokes in the reference frame of the fluid for small waves, so you just want to study little sound waves or shear waves, everything is fine. You see the waves and everything is good. But then you change reference frame and everything explodes. And here I'm talking about temperature that grows over a time scale of 10 to the minus 30 seconds. Okay, so I'm talking about incredible things. And okay, I'm trying to go ahead. Okay, and I would like to conclude the presentation by giving you an explanation, a little thought experiment to make you understand what is going on. And I will not solve for you the relativistic Navier-Stokes equations because they are too complicated, but I will consider a toy model, which is the diffusion equation, which will give you the idea completely, okay? So imagine this situation. There is this metal rod. Imagine it infinitely long, one-dimensional. Some heat is injected in this metal rod, and then heat propagates. Alice looks at this being at rest with the rod, and what she sees is the diffusion equation. The equation here on the up left, it's the one that everybody knows, right? Time derivative of the temperature equal second derivative in space of the temperature. But then Bob looks at the same thing, and he's traveling close to the speed of light. What does Bob see? It ruins all my moments of glory and wow. Okay, so what do I see is the following. When you solve the diffusion equation, the green function, okay, so the fundamental solution is a Gaussian, which has infinite tails. So this means that when you solve this equation, you always have a little bit of energy that propagates outside the light cone. This is supposed to be small, okay? It's rounding error. In physics, you don't consider this to be a relevant effect in practice. But unfortunately, it's there. So when you boost it, you change reference frame to the point of view of Bob, you will see that some heat exists before you inject it. Okay? Some heat propagates backward in time. And the amazing thing is that, think about it, heat is spreading backward in time and it is diffusing. But if you look at it going forward in time, you see the reverse of diffusion, right? You see concentration, focusing, the spontaneous formation of singularities. Indeed, you can prove mathematically that the boosted version of the diffusion equation is an ill-posed initial value problem because it is infinitely unstable. And I will just show you a couple of equations to give you an idea of what happens. It's a calculation that you can make at home. It's super easy, okay? So you take the diffusion equation, it's there, and you boost it. Usual Lorentz boost, nothing strange going on, and this is what you get. All of a sudden, you get a second derivative in time. This is the key. So now let's do this. Let's kill the space derivative. I focus on homogeneous solutions. Okay, 5 minutes, great. I will be in time. You focus on homogeneous solutions, so you kill the space derivative. And again, it ruins. Okay, you kill the space derivative, and what you get is this nice ordinary differential equation. You solve it. Boom. Here is what you get. A growing profile of temperature that grows exponentially. And here is the amazing thing. Imagine to send the velocity to 0. So you're moving very, very little. Okay, the piece of metal that is diffusing moves very slow. While here you have v in the denominator that goes to 0. So this exponential grows infinitely fast. It's an instability that makes the equations unsolvable in relativity. It's a problem you want to solve how heat propagates in a rotating neutron star. If the neutron star is not rotating, you don't have a problem because everything is at rest. But when it rotates, you need to consider that the fluid is moving, and then everything becomes unstable. And now we have an explanation for this. We have also some idea about how to solve this. It eventually involves, as you may expect from my talk, if it goes ahead. All right, so it, of course, involves relativistic thermodynamics. So there has been a huge amount of discoveries after the publication of my thesis, part of them made by me, other from other theoretical physicists. It's a new field of research, and it's extremely exciting to be part of it. We have discovered the Lorentz invariant theory of stochastic fluctuations. We found some bounds on transport coefficients, like the one of the speed of sound, but something more complicated. Also conditions on all phases of matter for stability and nice behavior, connection between a mathematical property of the equations of motion, symmetric hyperbolicity, and Onsager symmetry, the foundation of the relativistic theory of rheology, universality classes in such theories, and so on and so on. It's a lot of exciting things that are going on. And yet, relativistic Navier-Stokes still does not exist. And probably, I think, it may never exist in the way we imagine it. We may need to rethink completely the way we picture viscosity when we go to relativity. And this is the thing that I'm planning to work on in the next year to clarify this subject completely. So thank you for your attention. And I close here.
Thank you very much, Lorenzo. So maybe we have a few questions for you, which is why I didn't want you to escape so fast. Are there any questions in the audience? Yes, please, Lucio. Anybody here in the front here? Sorry.
So very nice and very interesting. I was thinking about the implication for numerical hydrodynamics. So if I'm trying to describe an accretion disk, and there are many models that people have published over the past 20, 30 years, does it mean that it's only correct when I solve the equations in the co-rotating frame?
Oh, exactly. That's a beautiful question. So here is the problem. Because of relativity of simultaneity, you can show that in relativity, an actual co-rotating frame does not exist. Because what you can show is that when you try to follow the motion of the fluid, you will find that you're trying to adjust hypersurfaces orthogonal to the perspective of the person that is moving. And you find that you never manage to close the loop. So you try to make a co-rotating frame, you follow, and you get at the beginning, the two pieces of surface, they do not match. So technically speaking, a co-rotating frame does not exist, okay? This means that we need to do something else. Indeed, it is quite interesting that there exist some simulations of accretion disks that use relativistic Navier-Stokes. They should explode, and they don't, okay? So this means that there is some numerical trick going on, which is one of the things that I'm planning to understand well, because people tell me, yeah, but look, I've been simulating the stability of accretion disk and they don't explode. What is happening? The math tells you that it shouldn't work, okay? But numerics involves a lot of approximations and assumptions. There are regulators, there are many effects. But there are alternative theories that one can use. There is this famous Israel-Stewart theory for viscosity. The problem is that the theory is viscoelastic. It's not just viscosity. It's something a little bit different from the physics that we have in mind, and this is why it's a little bit controversial. So it's one of the things that I'm planning to clarify. But thank you for the question.
There is still time for other questions, so there is one here. Thank you.
Yeah, one question concerning the heat diffusion. You can simulate it with a Monte Carlo, just particle colliding, and this way transferring heat, and then just transform Lorentz transformation.
Yes.
So, and nothing would explode.
Absolutely. Indeed, yeah. This is a really beautiful thing. So what is happening is this. You have, for example, the Boltzmann equation, right? Kinetic theory of gases. That is a perfectly fine theory. It doesn't explode. When you solve it, everything is nice. But now you want to create some partial differential equations to describe the temperature field and how it propagates. Now, the tricky part is that when you do the hydrodynamic expansion, you assume the gradients to be small. And so you make some approximation neglecting higher order gradients. But the problem is that it's precisely the higher order gradients that would save you from the explosion. So when you move from kinetic theory to diffusion, you create these unphysical explosions. They are not real, okay? They are just a problem of how you try to derive an effective field theory for a field called temperature from, for example, kinetic theory. And it's the reason why still 80 years and theoretical physicists are debating over the existence of Navier-Stokes or not as a system of partial differential equations, okay? You may think of Navier-Stokes in different terms, like you may say, okay, I have the Boltzmann equation, I solve it, and it will behave kind of like Navier-Stokes. But then you want to write some partial differential equations, and there is always some problem.
Thank you very much, Lorenzo. Again, congratulations for your award and prize.
Thank you. Thank you very much.
And
I would like, of course, to thank everybody who made this possible. Of course, my supervisor, the MERAC Foundation, and the institute where I did my PhD. Thank you very much. This prize is also yours.
Thank you so much, and good luck with your future projects. Bye-bye. So the second awardee is Julia Victoria Seidel. She will receive her award from the hands of Lucio, the representative of the MERAC Foundation.
It's a really pleasure to award the Best Doctoral Thesis MERAC Prize in Observational Astrophysics for Julia Seidel for her work on climate and atmospheric circulation regimes of exoplanets from high-resolution spectroscopic observations. Congratulations.
Congratulations. And we will hear a presentation from Julia Victoria Seidel on probing the atmospheric dynamics of ultra-hot Jupiters. The floor is yours.
Thank you, everybody, for coming. I want to especially thank Lorenzo for setting me up to fulfill all of the stereotypes of observers versus theorists. But before that, I, of course, want to thank the University of Geneva and very much David Ehrenreich and Vincent Bourrier, who were my supervisors for this work and without whom I literally wouldn't be here. I'm now a research fellow at ESO, so I want to thank the MERAC Foundation for bringing me over from Chile to be here with you today. So I'm going to talk about how we can observationally probe atmospheric dynamics, winds and weather of ultra-hot Jupiters, where ultra-hot Jupiters are Jupiter-like exoplanets that are very, very hot. So we're talking about 2000 Kelvin and upwards, which means that all of our molecules are dissociated into atoms and we get very, very beautiful spectral lines. Unfortunately, it's very hard to make extrapolations from the planet that we know best to ultra-hot Jupiters because that's Earth, which is neither Jupiter nor ultra-hot. That's great for all of us, I think we can agree. But if we look at what we know for Earth, so here on the y-axis, you have altitude in kilometers, and I think most of you will know the right side of this plot. So we know all of the different constituents of the Earth. We know CO2 probably a little bit too much at this point, how they scale with altitude, and also how the temperature and the different inversion works. Especially for the troposphere and stratosphere, that's where we talk usually about, that's weather. This is where most things happen that are interesting for humans. And then we have, going further up, the mesosphere and thermosphere, ultimately ending in the exosphere, that is the boundary to space. So the part of this plot that I think most of you will not be as familiar with is the other side of it, here in orange on your left, I guess, where you can see the atmospheric dynamics as a function of altitude. So most of you will still know that the lower atmosphere is governed by the Atlantic jet stream that we use for travel quite a lot, westerlies and trade winds that blow across, and then the big circulation cells like the Hadley cells and Ferrel cells. But then if you go further up in altitude, we still know quite a lot from inverse sounding. For example, we know that tides and planetary waves kind of churn material from the equator to the poles. It all gets recirculated via gravity waves and then goes downward via polar vortices. So all of that's nice. That's kind of the theory. And now we come to what we can actually observe for exoplanets, which is a little bit more rudimentary. So we can split exoplanetary atmospheres roughly into 3 regimes that I really want to drive home because I'm going to use it throughout this talk. So we're going to have the lower atmosphere, that's what on Earth you'd call weather. So millibar pressure levels, where as you can see from the references, we can actually say something about atmospheric dynamics and how everything is mixed. And then on the very other scale of this, from the nanobar, we have the nanobar level, which is the exosphere, where we are not collision dominated anymore, and we're really just like losing particles to space and the interstellar medium. And also there you can see from the references, apparently we can measure and we can learn something. That leaves us with orders of magnitude of pressure where there's just a question mark and me waving my hands and be like, okay, can we say something about the intermediate atmosphere? And my entire PhD work was basically a proof of concept study of what can we discern about atmospheric dynamics for this intermediate pressure range for ultra-hot Jupiters and for exoplanets in general. So I'm an astronomer who works in South America, and I give a talk in Italy, so I could not help myself to use the most infamous Italian kind of as a vehicle into this proof of concept study. So Cristoforo Colombo, some of you might know him, worked in Italy on a grant to find a new route to India, and most of you know the story that he had one too many Aperol Spritz and he bumbled across the Atlantic, and then he brought disease and destruction to an entire continent for a few centuries. But the more interesting part here is that not only did he make it across the Atlantic, but he also made it back. And that's, to me, much more surprising, at least with my sense of navigation. And the way he did this is actually quite ingenious, because they used the trade winds that blow closer to the equator westwards from east to west to go crossing the Atlantic to the Americas, and then they used the westerlies, which flow in the opposite direction closer to the poles, to go back. And this established an actual reproducible route that they could take over the centuries to go back and forth. And this has interesting implications. All right, we're working on it. The first one being, how did they manage that? Was that just blind luck? They traveled over and then were like, okay, let's just drive around until we find somewhere where it blows in the opposite direction? No. They actually used prior knowledge for their proof of concept study. And the prior knowledge was that exactly this kind of blow in opposite directions had been used before to travel to the Canary Islands. So in the local environment of Spain, this was a very known theme. So they basically just extrapolated from there and hoped that it would work again. And like this, we got hundreds of years of data of the seasonality, when they did their journeys, how long it took, where exactly they went. And that gave us the first catalog, basically, of the global application of the westerlies and the trade winds for Earth's atmosphere. So they used prior knowledge, they used reproducible data to learn something globally about a class of atmospheric dynamics. And this is exactly what I did for my PhD and what I want to kind of use to give you a bigger picture of what it takes to do a 4 years proof of concept study for something like this. So the first part is the data preparation. How do we actually observe this? How do we see the imprint of atmospheric dynamics? And then how can we actually be sure that we can trust our data sufficiently to make any statements on it? Then the second part is, of course, the prior knowledge. What do we know already about atmospheric dynamics, churning of atmospheres, etc., and how does this apply to the bodies that we want to study here? And then hopefully, with a little bit of luck, everything works out. Spoiler alert, I won a prize, so it worked out. And then I'm going to tell you a little bit about what I plan on doing in the future with this. So first, the data preparation. It's just a little sketch. Observers like sketches of what's happening when we sit at our very, very complicated 8-meter class telescopes. You'll hear more about instrumentation later on from Johannes. So we have on the left side the host star, and then on the right side, Julia sits in Paranal Observatory and looks at the star and observes it. And at some point, we get photobombed by the exoplanet. So a very small part of the light, about 1% or so, is blocked from the host star by the exoplanet, and an even smaller fraction, so 1% of 1%, we are basically rubbing 3 photons together at this point, they will actually interact with the atmosphere of the exoplanet itself before they enter our telescopes. So depending on where in the atmosphere the light interacts with these particles, we'll get an imprint on the spectral lines from this absorption. And this is what this looks like. So this is, I think it was probably the first observation in high resolution of the Fraunhofer D sodium doublet. This is kind of the yellow optical wavelength range. And I apologize to everybody in this room. I don't know why astronomers like to do that, but this is not an emission line. This is an absorption line that is flipped, because it shows you a very interesting thing. You see on the one side, the y-axis is absorption, and then on the other side, the y-axis is altitude. So just from the spectral line itself, we already get one of three dimensions. So we get the altitude just by looking at different levels of these spectral lines. Where were these particles when they interacted with this light? Now, what does that mean for atmospheric dynamics? So far, I haven't talked about atmospheric dynamics at all. I've just shown you how to detect spectral lines for exoplanets. So if we take three lovely particles in our atmosphere, sodium, let's say, and we want to follow them, and we say, okay, they're kind of getting evaporated, so they're moving radially outwards, and we have extremely, extremely good telescopes, and we can observe just these particles, then we'll see when they interact with the light, depending on their speed, we'll see different imprints. And this is because of the Doppler effect. And if you've gone around through Padua to do a little bit of sightseeing from all of the sirens and the honking, you'll remember that the Doppler effect basically means that depending on velocity, sound or light changes quite drastically. So in this case, if we have no particle movement at all at 0, we'll get just our yellow sodium absorption spectral line. But then if the particle in the line of sight moves away from us or towards us, the line will be slightly blue shifted or red shifted from its position. Now, as I told you, we're looking at exoplanetary transits. We don't have in situ probes like the guys from the solar system. I'm very jealous of that. But what we get is an overall image of the entire annulus of the atmosphere that we observe. So we can't see all of these instances by themselves. We see them combined as one global view of these interactions. Also, we have to integrate over the entire transit, so we get this picture integrated over various hours of observations, which means that instead of these wonderful shifts that we can attribute to direct Doppler effects, we get something that looks a little bit more like this. So it's an amalgamation of everything, kind of a weird, wonky line shape. And now the question and the proof of concept that I'm going to present to you is, how can we extract what actually happened in this atmosphere from this wonky line shape that we observed? And to now move away from a little bit more of a drawing understanding of this, this is what you have to do. So I wrote a code that first of all takes a forward model, hydrostatic equilibrium, and then it imposes a three-dimensional wind pattern together with a planetary rotation on it and provides a model spectrum. For that, we need some form of priors that build up our atmosphere. And then we use Bayesian statistics to do a likelihood evaluation on the data itself. Now, this is quite complicated, but the two questions that I want to highlight here for you today is, first of all, is the data that we put into this actually trustworthy? So are the 3 photons that we have extracted truly from the exoplanetary atmosphere itself, or does it come from somewhere else? And then second, what prior input is actually sensible? Because, I mean, I don't know about your universities, but in Geneva, a PhD is 4 years, and you just don't have the time to evaluate every single model for every single cell in all of the directions. So there has to be some physically sensible prior that you can put into this work. Okay, so let's look first at the first question, which for me as an observer is quite important, so the false positives. I think most of you that do observations will be familiar with stellar contamination and such, and also with telluric observations. I mean, I think we can all agree that it's nice to have an atmosphere on Earth, but sometimes it's also a little bit of a hindrance. Since we use sodium as a probe here, I want to talk about something a little bit more esoteric. So something can happen to our data that can contaminate our observations and make our line unreliable. So this is a a hot Saturn was 127. And what you see here is, again, the wavelength range of the sodium doublet with the normalized flux overplotted. And these are stellar spectra, so we haven't even extracted the planet yet. And if you look at the stellar spectrum, you see the wonderful 2 deep lines of the sodium doublet. You see some nickel lines around. But if you look at the zoom in of the bottom of this sodium well, what you expect is, well, it's supposed to be a void profile. So in the bottom of this well, you should get a nice Gaussian shape. And for regular night, that's exactly what you get. You get a nice Gaussian shape. But what can happen is that the telluric sodium layer that sits somewhat at the mesopause of our own atmosphere can get excited and will emit exactly at the wavelength of sodium. So this is in the observer's rest frame. It will emit, well, sodium. So we get this kind of bump feature that shouldn't be there. And this can happen either by using the lasers at the telescope, so, human-made, or it can happen if you're lucky enough to see a meteor shower that will also excite the atmosphere. And that's not really something you can plan for, that just happens. And if you don't look for this, or you're not aware of it, then you get an absolutely stunning result. If it would show. Yes, here it is. So if we don't correct for it, we get the absolute most deepest, most fantastic sodium detection ever created for an exoplanet. 1.5% of sodium absorption must probe all the way up to space. Wow, how great. But if we do the correction properly for this sodium emission from Earth, then our 3 photons that come from the exoplanetary atmosphere look quite different. So after correction, we're more back into the realm of what we were expecting from this type of exoplanet in the first place. So as an observer, the more you observe, the least trustworthy you find data to be. And this is kind of the case here as well. I just want to drive home one of the main points of my thesis, that it is crucial that you understand the data properly and you take care of all of the contamination sources before you go on and actually try to learn something about the atmospheric dynamics from it. Now comes the second part. So from here on out, you just have to trust me that the data is great. And now we're going to the prior knowledge. What do we actually know about atmospheric dynamics on extrasolar planets? So let's go first to planets. From the solar system, the closest to Jupiter-like exoplanets are obviously Jupiter and the other gas giants. And we know quite a few interesting things from jealous enough in situ observations, but also from theory and remote observations. So we know that the lower atmosphere at the millibar level is dominated by equatorial high-velocity jets. That's the heat maps that you see below, where we have these jet-like structures in the mid-atmosphere, and then there's also some evidence for cell-like circulation at mid-latitude. Unfortunately, Jupiter isn't really that compatible with ultra-hot Jupiters. We can't just take these measurements and be like, well, let's crank up the heat to 2000 Kelvin and see what happens. So we have to go and look at prior exoplanetary measurements as well. So here again, what I'm trying to do is bridge what we know from the lower atmosphere and what we know from the upper atmosphere. And in the millibar level for the lower atmosphere, from both theory, global circulation models, give it a second. It's about as fast as the software runs at the telescopes. Here we go. So for the lower atmosphere from theory, we know that super-rotating jets are quite common, as well as day to night side wind from the hotter part of the planet to the cooler part of the planet at around 10 kilometers per second. And since quite recently, we actually have also observational probes for this with the heavier metals that populate the lower part of the atmosphere. I don't want to get too much into the details here, just take away from this that horizontal churning of the atmosphere is something quite known for the lower atmosphere. And then if we go to the other side of the atmosphere itself, to the exosphere, if it would do it, that would be great. The mouse isn't moving. Ah, there we go. Okay. So if we go to the exosphere and we're at nanobab pressures, there we've had observational probes actually for quite a while. So there's the main constituents of the atmosphere. So we have Lyman alpha, NH alpha from hydrogen, and then we have helium as the other main ingredient that we can observe from space to study mass loss through these lines. And then from theory, we know quite a lot about planet-star interaction, Parker winds, etc., to properly understand mass loss. So we know that in the very upper layers of these ultra-hot planets that receive a lot of irradiation, that kind of get sandblasted by their star with photons, that we have this mass loss that happens. Now the question is, how does this horizontal wind in the lower atmosphere and this upper mass loss actually come together somewhere in the intermediate range of the atmosphere? And observationally speaking, we can probe this now with the sodium doublet. So this is the sodium doublet of the ultra-hot Jupiter WASP-76, again in the range of roughly yellow optical light. And in the gray data points here, you can see the original data that was taken with 1 night of the Hubble spectrograph, with 3 nights of the Hubble spectrograph at a 3.6 meter class telescope, and 1 night with Espresso at an 8 meter class telescope. The white points are just to guide your eye, but all of the retrievals happen obviously on the original data. And the first interesting thing that happened, and I think that is not appreciated enough for proof of concept studies, is first, does it work at all? So when we try to just put an isothermal atmosphere in there, pressure broadening, temperature broadening, no atmospheric movement whatsoever, then the fit to the data was actually incredibly poor. And then if you only added the horizontal winds that we know from the lower atmosphere, it was already somewhat of a better fit. This is what you see here as the blue model. So the finding one of my thesis was that without actually involving particle movement, we really couldn't explain the data quite well. But then if you move further and you go through different atmospheric dynamical models that you can use in your prior, then we found that actually the best fit that came agnostically from Bayesian statistics was to apply a day to night side wind that moves particles kind of with a temperature gradient in the realm 5 to 10 kilometers per second. And then for the intermediate atmosphere, so when we go beyond this millibar pressure, then we have vertical winds that actually transport material upward at really incredible wind speeds, up to 20 kilometers per second. So very, very strong winds. And this was a fantastic fit to the data, and you see it here in yellow. So the other two findings from albeit a small statistical sample were that zonal winds, so horizontal winds that are compatible with jets, so day to night side winds, in the lower atmosphere are actually also measurable with this technique. And secondly, that an outward streaming particle movement at high velocities actually happens much earlier, much lower in the atmosphere than we thought from observations of the outgassing of the exosphere. So there seems to be, this process seems to be fed from the intermediate atmosphere already, which was honestly very surprising to me at least. Now, what do we do with this? Okay, yay, proof of concept, it works. So for my postdoc, I'm now at ESO, at the European Southern Observatory, and I learned a lot about instrumentation and telescopes. And Espresso, as I told you, is installed in an 8 meter class telescope, but it has a little bit of a superpower. So you can actually feed light from all 4 VLT unit telescopes at the same time to the spectrograph, which means you get access to a 16 meter class telescope. And that means that all of a sudden you have data quality with a signal to noise ratio that's so high that first of all, you spend 2 years of your postdoc, you being me, on trying to find out new contamination sources that you have to think about that could possibly impact your data. But it also means that you don't have to integrate over the entire transit anymore, but you can separate out different chunks of different viewing angles where you see different parts of the exoplanetary atmosphere. And so you can pinpoint features that are visible at different parts of the surface. And this means that, for example, in this work, we could show that there is a jet stream in the lower atmosphere that is roughly restricted to 30 degrees in latitude, which is somewhat similar to what we see in theory from global circulation models. And if you've heard the talks by Gail Chauvin and by Jane Birkby yesterday in the ELT session, then you'll realize that this high signal-to-noise ratio data is one of the pathways to prepare for the upcoming ELT, and this is what I'm hoping to spend my time on in the next few years. So as a summary, I provided a proof of concept study how we can provide a new observational probe for atmospheric movement, and we found that vertical particle movement seems to also happen in the intermediate layers of exoplanetary atmospheres for ultra-hot Jupiters, which was quite surprising. Thank you so much.
Thank you. Thank you very much, Julia. Now it's time for a couple of questions if there are in the audience. Let me see if I see raised hands. Are there any raised hands? Yes, there is one there. Yeah, thank you.
Very nice work, Julia. Can you maybe say a few more words of how you modeled actually the winds?
Sorry, can you repeat that?
Yes, I would like to know more how you modeled the wind structure of the planets that you
Right.
interpreted.
Yeah, that's actually a very good point. So if you're used to global circulation models, then it's rather crude. So what I do is I assume a pressure and abundance structure that obviously, since we're using ground-based data, we can't use any absolute pressure. So we don't really know where the base is. So I'm assuming wide light radius, as most people in the observational realm actually do, and I scale from there upwards. This is something I hope to change soon by incorporating space-based data. And then I create a 1D structure in pressure and abundance, and I overlay this with a 3-dimensional grid, that's so to say, so cell-like structure for the entire atmosphere. And only the winds are truly 3-dimensional. So then I actually calculate for each quadrant of the atmosphere, so to say, a lower layer and an upper layer with a different line of sight velocities. And I leave the base where the change between those two atmospheric regimes happens as one of the free parameters for the retrieval.
Thank you for the answer. Is there any other question in the audience? Yes, there is one again in the front here. Thank you.
Do I understand correctly that this part of the atmosphere is then magnetically dominated because the pressure is so low and you get such high velocities? So it couldn't just be hydrodynamics. It's highly, highly supersonic.
Yeah, so I think this is a very interesting point. So I'm an observer. I provide basically what can you get from the observations, how good is the data quality, and what kind of error bars and what kind of global statements can you make. But I think it's very important then to follow up on this, and a few of my colleagues have done this in the meantime, to see what's actually the reason for these Doppler shifts that we see for the wind speeds that I retrieve. And one of the theories that they currently explore is actually the high ionization rate of this part of the atmosphere and the magnetic fields that they see there. But that's very much still a work in progress, I'd say. And also, I don't incorporate it, but there are a few codes that don't do retrievals on data like I do, but they do simulations with true hydrodynamic assumptions for the upper atmosphere. And we're also currently working on where do these two actually intersect and where's kind of the switch happening when we have to start using hydrodynamical codes, etc. For a postdoc, I guess.
So thank you very much and congratulations again for your award and prize. Thank you, Julia. And our next and last awardee for the day is Johannes Heyl. So he will receive his award from the hands of Lucio, representative of the MERAC Foundation.
So it's a pleasure to award the 2024 MERAC Prize for the best doctoral thesis in new technologies, computational, to Johannes Heyl for his work on machine learning-based techniques to understand astrochemical processes in the interstellar medium. Congratulations.
And we will hear from Johannes a presentation on statistical and machine learning approach to the study of astrochemistry. The floor is yours.
All right. Thank you so much. First of all, I'd like to thank the MERAC Foundation for this award. It's quite an honor. I'd also like to thank the organizers of the conference. I've just had a wonderful time attending some fantastic talks. And then finally, I'd also like to thank my supervisor, Serena Viti, who's in the audience, for being a fantastic supervisor over the last 4 years, and I look forward to our continued collaboration. Overall, I guess my talk is, as mentioned, is all about taking a statistical and machine learning approach to the study of astrochemistry. Just a bit of an overview. I'll start off by introducing astrochemistry and why and what specifically I was interested in. I'll talk a little bit more about looking at reaction rates and on grain surfaces in the interstellar media and how we can take a Bayesian inference approach. I'll follow up on this by identifying a specific issue with the Bayesian inference approach and how we can rectify it. And I'll then change track slightly and focus on this idea of machine learning interpretability and how it's a general purpose tool that we can use within astrochemistry. And I'll end with some concluding remarks. All right, just bear with me. Technology. All right. So why astrochemistry? So what is astrochemistry? It's really fundamentally it's an attempt to understand the chemistry that occurs within the interstellar medium. And why is this of importance? Well, molecules help us understand what's actually going on, whether this be what's going on with the physics, what's going on with the chemistry. And different species and abundances can trace specific components or evolutionary stages, or even tell us a little bit more about what's going on. And there are a few different actors that we can consider: starlight, cosmic rays, dust grains, and gas dynamics. I'm going to focus on dust grains. So just a little bit about grain surface chemistry. You see a picture here. There's a veritable zoo of reaction types that can happen, and it's a very rich environment overall. So definitely worthy of several PhDs in and of its own right. And as you can see, sort of the different kinds of reactions that can take place are very varied. So you've got the standard molecular formation where you've literally got these these molecules moving along the dust grain, and then they react when they encounter each other. You've got some radiation-based ones, and you can introduce gas phase interaction. So something comes in from the gas phase and reacts with a molecule on the surface of the dust grain. And so interchangeably, what I'll end up doing is I'll end up referring to the ices, which refer to these several layers at the top. And I sort of use that term sort of naturally. I'll talk a little bit more about grain surface chemistry. Now, this is by no means a straightforward topic to try and understand, because modeling what's going on involves integrating ordinary differential equations that are very coupled. Because fundamentally, when you're talking about chemistry, you're talking about chemical reaction networks, where you've got different species reacting with all sorts of things. So there's no straightforward way to understand what's going on and what the influence is of any specific parameter, whether it be physical or chemical, like temperature. So this introduces an element of nonlinearity to further complicate our understanding of the relationship between any initial parameters and chemical abundances, which are the outputs of these sort of computational codes. So one approach that we can take to understand the chemistry on grain surfaces is actually estimate what are the reaction rates. And if we know what the reaction rates are, then we know, well, what's going on, what's most relevant, what are the molecules that are particularly salient in our understanding of our observations. And there is quite a bit of uncertainty surrounding these values. I mean, obviously, lots of laboratory work has gone into better modeling this, but there remains some uncertainty. So Bayesian inference can be used to estimate these reaction rate parameters using our observations we have from dark clouds, which are quite a rich environment for some of the stuff we've considered. We use our in-house astrochemical code UCL Chem, which is also open source, to model a collapsing dark cloud. And we take a standard gas phase network and a grain surface network that came out a few years ago that actually demonstrated how you could form the amino acid glycine from atom-atom addition. So you can literally imagine it's composed of all the different atoms just basically reacting and slowly building up to form gradually larger molecules until you reach glycine. But glycine isn't really the focus of this talk. So our code, UCL Chem, what we can provide as an input is some vector of reaction rates k, if the cursor decides to cooperate, and it outputs some molecular abundances, capital Y. And you can recall Bayes' law, and we want to say, given some data, given that we know that there are certain species with certain level of abundances listed in this table over here, can we get some probability distributions on our reaction rates, k? And we can introduce some prior, and later on I can also discuss some of the issues with that. We assume our data is normally distributed, which is reasonable. And we find that when we try and estimate the 49 reaction rates in our grain surface network, the algorithm simply does not converge. You can really try and reason with the algorithm. You can beg, you can pray, nothing really works in the end. So we clearly have to come up with some other means of estimating, because we just, as you'll see, we just do not have enough data. We've got seven data points, and we're trying to estimate 49 parameters. It's very much results in a very degenerate regime, so we have to come up with some other approach. So what I ended up doing in the PhD is, instead of just assuming that these reaction rates are just numbers, can we try and understand the physics of them, of the actual mechanisms and the formalisms that underpin them, in order to maybe exploit something and hopefully make this a more tractable problem. And so it comes down to making use of what's called the Langmuir-Hinshelwood mechanism, or just grain surface diffusion, where the rate at which two species A and B is given as follows. You've got some, like a prefactor, some constants, and really what's important is these so-called hopping rates. The hopping rates of A and the hopping rate of B. And that's given by, so that's effectively like literally these molecules are moving along the surface of the grain. And so it just basically, it gives you a sense of like how fast they move. Fundamentally, at a fixed temperature T, the hopping rate of a species X is defined as follows, and it's dependent on this parameter called the binding energy of that species. So oxygen has a binding energy, O2 has a binding energy, H has a binding energy, H2 has a binding energy. And it's really, this binding energy effectively is a measure of the mobility of the respective molecule. And what you find is that if you actually look through the literature, that the various molecules will have very different binding energies. So this, at 10 Kelvin, this exponential dependency of the hopping rate on the binding energy means that one species ends up completely dominating the reaction rates via several orders of magnitude. And as a result, we don't actually need to determine all of the hopping rates. We just need to know the binding energies of the most reactive species in each reaction. And you're going to end up with sort of a handful of suspects. It's going to be H, H2O, and N, and a few others. And so we end up, in this case, for our original network, which had 49 reaction rates, we can actually determine all of these 49 reaction rates, we can estimate them rather, by just estimating 14 binding energies. And when we do this, we obtain some posterior distributions. There are a few distinctions here, which I can go into at another point. But crucially, we end up with something that converges, that is where the nested sampler converges. And if we take the joint distribution and then we plug it back into our forward model, remember UCL Chem takes some reaction rates. We have the binding energies, so we can calculate the reaction rates, so we can put it into UCL Chem and get some abundances. We observe that the time series of our molecular abundances actually do end up matching quite nicely with the original data that we had, which is reassuring in and of itself. So now, that's all well and good, but some of you may have noticed that the binding energy posteriors, I mean, the fact that we got them is fantastic. They still continue to have high variance despite this significant dimensionality reduction we performed. And I go back to something I addressed at the beginning, is that we don't have enough sufficiently constraining observations. So there's two aspects to this. One is we just need to detect more molecules. And two, even the observations we do have simply are not constraining enough. Some of them are only seen to be greater than 0 at, say, the 1 sigma level. So that's not, they've got very high relative errors. So now we want to take a different approach and see, can we identify the species whose detection would actually help further reduce our binding energy variances. Because remember, the binding energies help us determine the reaction rates. And we make use of an information theoretic algorithm called the MOPED algorithm that actually has found use within cosmology and particle physics, and we apply it to our problem here. And so the aim is, we have a chemical network. We want to determine which of the M species in our chemical network need to be prioritized for future ice observations to best constrain the posteriors for our P parameters. And the algorithm is linear compression, and not going to go too much into the details, but the long and short of it is that for each binding energy, we can say how important each molecule in our network is in sort of affecting its value, sort of in hand-waving fashion. And we obtain what are called these filter sums, which we can then use to help rank all the species in our network by. And so effectively what we end up with is a single number for each species in our network, and a single number that tells us how important is it for us to measure the abundance of that species in reducing the variance of our binding energy posterior. So we've got a nice bar graph here, and so we've got a ranking, which is great, but this in and of itself is not enough, because a lot of these species simply won't be abundant enough for a telescope such as JWST to pick up on. So if it's predicted to have an abundance of 10 to the minus 20, well, but it's the most important molecule, well, that's great, but we're not detecting that at present. So we have to now juggle a number of different constraints. We have to juggle the additional constraint that we want species whose predicted abundance is going to be above some level, right? Because if we're going to feed this to observers, this has to be something that's actually useful to them. So what we do now is we plot the filter sums from before. I didn't plot all of them, but I sort of clipped the x-axis at this abundance of 10 to the minus 8, and I then plotted on the x-axis a maximum likelihood estimate of the abundances of each of those species. So again, a lot of the molecules just didn't make the cut, because we said that we found that their MLE abundances were far too low. But now we've got a sense of, okay, these are sort of the species that we have in this scatter plot that are relatively abundant and have large filter sums. So they're important in determining the binding energies, and we're likely to spot them. But there's now a third constraint that we have to consider, and obviously something like JWST has a specific range of wavelengths on which it operates. So we have to account for the so-called detectability. The species that we recommend must have modes that are in the appropriate wavelength range. And so a number of species end up satisfying this criteria. There's 3 criteria: H2O, CO2, NH3, CH4, CO, methanol, formaldehyde, HCN, and H2S. And one thing that you might notice is that some of these species might be familiar. We already had abundances for these to begin with. So again, what does this say? This says that actually these species could warrant improved detection, so sort of more tight error bounds on their abundances, which, that's also a useful thing to know, because it goes back to this idea that we had to have enough sufficiently constraining abundances. So this paper that came out was prior to JWST launching, and then actually the JWST Ice Age mission ended up detecting a number of these molecules as well. So then this can be then fed back and then used to further constrain our binding energies, which, as you recall, helps us constrain our reaction rates. And now, as I said before, I'm going to switch gears slightly, and I'm going to talk more about a general problem in astrochemistry. And it is maybe not unique to astrochemistry, but in general, understanding the relationship between input parameters and model outputs is challenging when you're utilizing some computational code. And of course, there exist traditional approaches of using grids of models, but that's limited by computational cost. You have to take into consideration the granularity with which you sample, and even then you might miss a very interesting window of the parameter range where some of the interesting physics and or chemistry is happening. So we want to get a sense of what's called the feature importance to make use of the machine learning vernacular. The feature importance, which tells us, okay, how much does a specific parameter contribute to the model output? So how important is, say, the temperature in determining that H2O has this abundance in the ISM? And why is that useful? Because it's crucial for interpretation. All right. And we can use something called SHAP, which has its roots in game theory, to enhance our understanding of chemical code outputs. And so we made use of our code, the UCL Chem, for some time-dependent modeling. And it consisted of two phases, an isothermal collapse of a gas cloud, followed by some protostar formation. And we varied a number of different parameters, which you can see, the density, metallicity, radiation field, cosmic ray, and the final temperature of the protostar. And we wanted to see, okay, what happens now with a bunch of different molecules and molecular ratios. And as you may recall, I said at the beginning that these molecules are interesting because they can trace certain behaviors of the system. For example, one well-known case is the HCN to HNC ratio, because that is that is sort of known as the cosmic thermometer. And is machine learning interpretability able to demonstrate this? So this is what's called a B-swarm plot, and can be relatively tricky to understand the nuances and intricacies of it. But effectively, the take-home message for all of you is, you can imagine this is ranking the 5 different parameters, physical parameters of interest, in terms of how important they are in predicting the HCN to HNC ratio. So just the most important is temperature, followed by metallicity, and so on and so forth. I mean, that's all well and good. It does seem to support this idea of this ratio being serving as a proxy for a thermometer, for temperature. But can we now explore this some more? So what we're now going to do is we're going to plot what's called the SHAP value. And for all intents and purposes, I think you can sort of imagine it represents, it's proportional to the value of the ratio. I think that's sort of the take-home thing. And we're going to plot how this SHAP value, so how does this ratio, how is it affected as a value of these physical parameters? And we get some plots here, and we can see that some of them, like the density, the cosmic ray, and the UV, just have no effect. That's maybe not too surprising. But the temperature, crucially, it does have one. It does have a strong effect, as does the metallicity. And the temperature, actually, we see that it has this interesting shape. It has an inflection point at about 80 Kelvin. When we match this up with the work done previously by Hachar et al., they modeled this as a piecewise linear function, so with two pieces. And we actually were able to match their what they observed in terms of the temperature dependency on, the dependency of the ratio on the temperature. And that fundamentally, that you can then go and think about this chemically. Why is there this inflection point? It's basically because of specific reactions dominating at certain points. We can also then, instead of just looking at this globally, we can also look at individual data points and look at the influence of, okay, when the temperature is 151, what is the effect on the ratio? So we see that the ratio is about 2.6. The temperature being 151 massively contributes to that. So it's about a quarter of the reason for it, followed by the metallicity. However, when the temperature is 15, it's responsible for the ratio being 0.5. It massively decreases the ratio. And so we can come up with these additive explanations for what the role of each parameter and how they're sort of competing with each other as they take different values. Oops. And then some concluding thoughts. In astrochemistry, we consider nonlinear relationships between physicochemical input parameters and molecular abundances. Binding energies are crucial to understanding grain surface chemistry. There's a lot of work being done. We can estimate these with Bayesian inference. It's much easier than just estimating the reaction rates. They still have high variances because of the lack of data, so further ice observations are required, and we can use an information theoretic approach to sort of identify which species should be prioritized. And we've also demonstrated that machine learning interpretability is useful in providing some intuition into the relationship between inputs and outputs, and not just globally, but also for individual observations. So yes, thank you.
Thank you very much. And it's now time for questions. So there is one in the middle here.
Thank you for your nice talk. My question is, can you comment on the applicability of your machine learning approach to the interpretation of photochemistry in planetary atmospheres?
Yeah, so I mean, this is very much a general purpose approach. So I don't know exactly what for the specific code what your input parameters would be, but yeah, you could in principle just you provide it with a certain amount of sort of training data, and it would then come up with these additive explanations for what the role of each parameter has under specific conditions. So you can really use it to like look at tracers, to we looked at a more global range of parameter values, as you may have seen. But if you want to study a specific system, yeah, you can definitely say, okay, the reason that we get this abundance is because of this amount of radiation versus this density, and you can sort of come up with these explanations.
Thank you. Is there another question in the audience? There is one from Ignasi up there. Thank you.
Good talk and congratulations. So I'm curious, have you compared the performance of your method, your machine learning method with SHAP with something simpler such as principal component analysis?
Yeah, so I mean, the idea is, yeah, principal component analysis, yeah, you can identify the, sort of like what's responsible for the most variance. But what I think it struggled with a little bit when I tested it out was looking at, looking at like local explanations. And I think, yeah, some of the issues with sort of the nonlinearity meant that sort of the explanations, when we compared to real results, just weren't really up to snuff. So this is quite good at looking at sort of a variety of different cases.
Oops, there is a question here in the middle. Thank you.
Thank you very much. That was a lovely talk. There is a third leg of observations and models, and that is the laboratory studies. And there's a very extensive, as you're well aware of, astrochemistry network. But that astrochemistry network is also moving in a direction of applying systems chemistry, which matches very well to what you're doing in the machine learning. And Sergio Oppolo, who's the glycine who you mentioned, it's very useful to discuss with the experimentalists what would be an ideal case study. The HCN, HNC may be one, but there may be others. So I think it'd be very useful to have those conversations within the community.
Yeah, I definitely agree with that. So I've been attending some workshops to look at the binding energies, to look at how these methods might be relevant to chemists who work in the lab. But yeah, so we're like further work is actually going to be looking at speaking to actually to trying to reproduce not just observational trends, but also laboratory experiments, and sort of seeing how they match up. Does the intuition work? Because fundamentally, this is just a tool. At the end of the day, we just want to try and make sure that the science makes sense to the experimentalists, to the observationalists, to the theorists, and the computational scientists. So yes, thank you.
So thank you very much, and congratulations again for your prize, Johannes. I think that all our awardees really owe a round of applause. So congratulations to the three of you. We would like to say that this year has been a very, very rich in terms of quality, number of applications for the PhD prize.
Yeah.
And
yeah, in fact, the MERAC Foundation is really happy that we had really a record number of submissions this year, as Nabila was saying, and we would like to remind that this coming year is the turn of the other prize, the prize for Best Early Career Researcher. This is awarded to scientists that have at most 10 years of career after their PhD by the time of application, which will be next fall. And of course, it's supposed to be awarded for the work done after the PhD. So it's complementary to the prize that has been awarded this year. And it's also important to recall that both the Best Doctoral Thesis Prize and the Best Early Career Prize come with a generous grant that the MERAC Foundation is providing. So there is a project grant that is associated with both prizes and can be requested upon a very simple application by the winners, which is at least of order 100,000 K. So it can actually help starting off your career as a group leader by hiring a collaborator, a student, if you are an early doctoral thesis prize winner, or a postdoc if you are in the later career prize category. So please wait for the announcement by EAS for the call that will happen in the fall.
And I will just take a few seconds to remind that these prizes are open for early career scientists and PhDs within Europe, that the nominations come from members of EAS. So this is an encouragement for you to become a member if you're not already. They also ask for 2 supporters, one of them being an EAS member. So don't hesitate to nominate your colleagues. And the prize committee and myself will be very happy to go through the application and nominations of such high qualities that we had in the past. Thank you very much, and let me hand over the mic to the rest of the panel session.
So now it's time for the last presentation that is given by Professor Richard Ellis, and it will be about the progress and the surprises in early studies of early galaxies or with JWST.
Well, thank you very much for the opportunity to tell you about the exciting progress that's being made with the James Webb Space Telescope. It really is a truly exciting time, and we've heard through this week astonishing results that are transforming our view of the early universe. Sometimes I think it's interesting to just take a trip back to how we got to this point. This is a plot of the most distant spectroscopically confirmed galaxy as a function of publication date. And when I started my career as an undergraduate in the late 1960s, the most distant known object was 3C295, a radio galaxy, which had the mind-boggling redshift of 0.46. And as you can see, it held that record for 15 years or so. And it was actually noteworthy at the time because people realized that we were looking back at that time to a galaxy that was being seen before the solar system was born. But if you look at the progress since then, it's truly been amazing. And now we are at the point where we're measuring spectra at redshifts of over 14. So this is seen then when the universe is only 300 million years old. I was originally, I was a member, the only European-based member of the committee, HST and Beyond, chaired by Alan Dressler, that wrote this report, HST and Beyond, that proposed the idea of what was then called the Next Generation Space Telescope. If you haven't read it, it's publicly available. You can Google it and find it. And it's actually very visionary because there were 2 pillars. One, perhaps naturally, was looking to the earliest galaxies. That was a rather obvious goal of what became JWST, because we'd seen with Hubble, you know, Hubble was in full swing doing the deep field, and we'd seen the excitement of looking back in time with Hubble. But the other pillar was exoplanets, and since, you know, we've heard a lot about exoplanets this morning and through the week, that was in many ways a more visionary aspect of this report, because at that time, the subject of exoplanet studies was really in its infancy. I was privileged just before lockdown, the last trip I did to the United States in February 2020, to go to the Northrop Grumman facility in El Segundo, Los Angeles, to see James Webb in the space facility there. And you can see it here. It's was really almost a religious experience to see this massive telescope ready for launch. So the purpose really of this talk is to, here we go, to search for the earliest objects. So let me give you a sort of sketch for the non-experts of why this is exciting and where we are. So the idea generally is when the universe is only 200 million years old or so, the universe was very dark. There was the thermal glow from the Big Bang that pervaded the universe at that time, but there were no stars or galaxies. There were just hydrogen clouds. And those hydrogen clouds were drawn gravitationally to the dark matter. The dark matter had already fractionated from the expansion of the universe at that early time. And those gas clouds collapsed. And of course, as they collapse, they heat up and they form nuclear ignition. And the universe is bathed in starlight for the same time at that time, for the first time. Now, those stars are much hotter and more energetic than stars of the same mass in the Milky Way because they don't have any line blanketing. They don't have the chemical elements other than hydrogen and helium in their atmospheres. And so they emit copious amounts of ultraviolet light that can ionize hydrogen and produce these ionized bubbles that you see in this illustration here. And as time progresses, those ionized bubbles grow and become more numerous, and they overlap. And then eventually the universe is completely ionized in intergalactic space. And we've known that the universe is in intergalactic space is fully ionized since the 1960s or so. So the challenge at the frontier is very simple, really. The questions are really, when did all this happen? Let's see if this comes up. When did all this happen? You know, can we witness a galaxy that's emerging from darkness? You know, would we recognize such an object? And the role of black holes, we've heard earlier today from a very nice talk by Hannah Ubler. You know, how did all these quasars develop? Billion solar mass black holes by a redshift of 7.5, which is only about a few hundred million years later. So these are the questions that we've been hearing about during the week, and I'll attempt to summarize the results today. I'm going to basically show you firstly what the capabilities are and why James Webb is so special. Sometimes, you know, it's mentioned that James Webb is a successor to Hubble. That's strictly not the case. It's more like a superb successor to Spitzer. We've seen, of course, it has a larger aperture than Hubble and Spitzer. It has a better angular resolution than Hubble, but it's its infrared coverage that is most important, particularly for studies of early galaxies. So we go beyond the horizon of 1.6 microns of HST to greater than 10 microns with MERAC. Interestingly, it also has a very wide and helpful array of filters, including medium band filters whose width is narrow enough that you can actually combine the actual photometry and detect the presence of strong emission lines without doing spectroscopy. And that's been very advantageous in panoramic imaging with James Webb. But I think we would all agree, those of us working in this area, that the biggest improvement is because of the aperture. We have spectroscopy. We have a number of spectroscopic capabilities on JWST. And, you know, because of the infrared coverage at high redshift, we're able to trace the very familiar rest frame optical diagnostic lines that we've been studying for decades with ground-based telescopes. So over a period of only less than 2 years, there's something like over 200 articles on the archive studying early galaxies. So it's really quite a challenge to summarize all of this, but I'll do the best I can. So I want to start with, I'm going to go through a number of highlights. Some of the work is work that I've done with my collaborators, but much of it isn't. and I'll try to give credit where possible. One of the most immediate things that came out of the first public data sets, the early release science and other public data sets that were available soon after scientific operations began, was a census of galaxies beyond the horizon that's possible with Hubble. So what you see on the y-axis here is the co-moving number density of star-forming galaxies per cubic megaparsec as a function of redshift on the bottom and the age of the universe on the top. And the dashed line, this black dashed line, shows the most distant horizon that we were able to get to with Hubble, a redshift of 10.6. Now, just before the launch, there was quite a lot of controversy in this region around redshift 9 and 10 as to how steep this decline was. And unusually, and this is not often the case, many observers were keen to follow the theoretical predictions. This doesn't happen very often in observational astronomy, I should say. And so, there was a general feeling that the data would fall off as one goes to higher redshift following this theoretical curve. So what is this theoretical curve? Well, the theoretical curve basically is the concept that, as the universe expands and ages, so dark matter halos grow. And if one assigns baryons to these dark matter halos with the cosmic baryon to dark matter fraction, then you can estimate the amount of gas that's available to fuel star formation as a function of evolving time. And the idea here was if the star formation was a constant efficiency, in other words, you have a certain amount of gas and that a fraction of that forms into stars at a given rate, then you could predict, how these observations change with time. And indeed, this model fitted remarkably well at redshift of up to 8 or so. But there was controversy in the community as to whether the curve was going to fall consistent with this with James Webb or not. Some of us looked at the ages of stars in some of the most distant galaxies and thought this wasn't the case, and there would be galaxies beyond a redshift of 11 and 12 in James Webb data. So the first big story that came out more or less immediately by many groups listed here is that indeed there are galaxies beyond the horizon, that were detectable immediately out to redshifts of 13, 14, and so on with James Webb. Now, I'm going to come back to why is it that the theory is wrong and what is the explanation for this additional population of luminous galaxies that aren't obviously consistent with this theory, and I'll come back to that in a moment. So this particular plot comes from the collaboration I did with the University of Edinburgh with Derek MacLeod. So if I bring you up to date on this census now, there are two rather complementary programs that have been completed very recently. One is, on the left, is the PRIMER survey. This is the largest cycle 1 panoramic NIRCam imaging. So it's 400 square arc minutes. So that's 10 times the area that we saw in that previous figure that I showed you. It's just astonishing to me. 2,500 galaxies beyond a redshift of 8.5 in this data set. There were 7 in the Hubble Ultra Deep Field in 2012. So that gives you some idea of the progress that's been possible. If you look at the bottom panel here, this is the result from Callum Donnan, who's shown there. And you can see, again, the continuity in the star formation rate density with this tantalizing possible decline, very marginal 1 sigma at the moment at redshifts of 14 or so. Now, complementing this panoramic 400 square arc minute survey is the JADES Origins field, which was a cycle 2 program by the JADES team, which is essentially the first sort of super ultra deep field taken with James Webb. It's 2 fields totaling 9 square arc minutes, so very small compared to the PRIMER 400 square arc minute, but pulled out all the stops in very long exposures, probing with the capability of NIRCam over these many filters that I showed you, sensitive to galaxies between a redshift 12 and 20. They located 8 galaxies beyond a redshift of 11, but the final one at redshift 14, no galaxies beyond a redshift of 15, but the number that they could find is governed, of course, by the very small size of this field. And so this absence of any galaxies beyond a redshift of 15 is consistent, given the uncertainties, with the decline rate that you see there. So in the early days, a lot of these galaxies that are placed at these redshifts were determined from photometric data. That is, they're photometric redshifts whose spectral energy distributions were used to locate these objects. And basically, since then, spectroscopy has been catching up. This is really frozen completely. I don't know. Let's see. And broadly speaking, within, with one or two very easily understandable exceptions, the spectroscopy has verified the photometric redshifts very well indeed. And I just show you two of the spectra here that I think are noteworthy. The one on the top from Andy Bunker, GNZ11. This is a historic, very famous object discovered by Pascal Oesch. It was the most distant object detected at the pre-launch of James Webb at redshift of 10.6. Beautiful spectrum, we can see, with many emission lines, a very clear Lyman break that, of course, is a clincher in estimating the redshift. And the object below from Stefan Candiani at redshift of 14.3. Again, a beautiful spectrum by the JADES team. I think it's noteworthy in this particular object. You see, it's right next to a galaxy that a redshift of 3.5. So it took a real perseverance to believe that this object was completely independent of an object that's only less than half an arcsecond away. And that perseverance really paid off, I think, in this particular spectrum. So look at the parameters here. These galaxies are just a couple of hundred parsecs across. So that's 50 times smaller than the Milky Way. Yet they're belting stars out. They're forming stars at 20 solar masses per year. So that's 20 times the star formation rate of the Milky Way. So these are really energetic objects seen at a very special time. What's going on here? Look at this figure from Carniani's paper, which I think is very illustrative. So what you see here is the luminosity of the galaxy increasing upwards on the y-axis against redshift and age of the universe. And the two spectra that I showed you, GNZ11 and then this galaxy at redshift 14, are outliers. They're more luminous than any galaxy later in this plot. And so what that's telling us is that there must be some new time-specific physical process responsible for the intense emission from these objects. So there have been many explanations, and the jury is still out. We've heard at this meeting, various possible explanations for this period where galaxies are superluminous. One is that maybe these galaxies are dust-free. Remember, they're very compact. They're forming stars at a very ferocious rate. So maybe the radiation pressure from these galaxies, given their compactness, is sufficient to blast any dust out. And as the galaxies assemble, the dust eventually settles there. And so, maybe they're just more luminous because they're dust-free at this time. Another possibility is that we're seeing them at a special time. They can't sustain this luminosity for a very long time. Maybe we're seeing them at a peak of a burst, so that normally for their mass, they would be less luminous. And so let me just address these two hypotheses. Dust, of course, can be detected by the presence of its effect on the ultraviolet continuum. So, there's good data now from spectra gathered by two groups, Robert Sporsani in Geneva, Heitz et al. In Copenhagen. And they've measured, both individually and through stacks of spectra, the slope, the power law slope of the UV continuum, beta, which is, bottom down here at lower, more negative values of beta corresponds to steeper slopes. And you can see that indeed there is a more or less monotonic trend that as one goes to higher redshift, the slopes are getting steeper. we can imagine a limit for this, which is defined by, an instantaneous star formation population, an instantaneously formed stellar population, with a given IMF. But then one has to imagine also that at the very early stages, these hot stars also produce nebula continuum in the surrounding gas. And, broadly speaking, what we see is that we basically move down to a value that's equivalent with being dust-free. But it's a very gradual trend. It's not as if there's something spectacular happening just in this early period where these galaxies are superluminous. Indeed, if one looks more closely, the very earliest galaxies are slightly redder. The data sets are still very small, but this may be actually telling us that the nebula continuum is actually quite steep, because the nebula continuum generally is redder than the stellar component. So this idea of bursty star formation has been studied in more detail at slightly lower redshifts 7 to 9 or so, where you can look in this top left panel at the flux in oxygen-3 emission, this 5007, well-known optical line with H beta. And for the most luminous galaxies, you can see they have a higher equivalent width of O3 and H beta compared to the subluminous component, which has led to the suggestion that the subluminous component are in a down state in their star formation activity. And the luminous objects may have a component that's been upscattered by recent activity of star formation. Simulations support this idea. Generally, the idea is that there's a scatter in the relationship between the ultraviolet luminosity of a galaxy and where it lies in its halo mass or stellar mass. And if you apply this scatter, then it may at least make some contribution to boosting the visibility of these early galaxies. And so that seems to work reasonably well, although it turns out it's getting harder and harder as you go to higher redshift. So I have to move on. I'd like to turn to active galactic nuclei and return to this question of how did the black holes assemble? And really, we need to find them in the epoch of reionization, and it's very challenging. Basically, three ways that we can do this. One is we can use time-honored spectroscopic techniques and look for the broadline regions in the spectra. Generally, X-ray detections are too challenging, even with the Chandra satellite on individual galaxies. And variability, which is, of course, another way in which we can look for AGN activity, does require a very long time scale, because remember, when you get to redshifts greater than 7, the time dilation is very significant. So we really only have the baseline with Hubble data at the moment to do that. Here's a very good example of what I think is a pretty convincing broadline AGN at a redshift of 8.5. You can see the spectrum here, and I zoom in on the breadth of H beta and the narrow emission lines of O3. Now, this mass basically is, of course, highly uncertain because it's based on the assumption that the broadline region is in virial equilibrium. So it's generally understood that this mass estimate can be overestimated, but probably not by more than a factor of 2 or 3 or so. And already the mass of this black hole is 30% of the stellar mass of the galaxy. So, we do need better precision on understanding this offset from the relationship that we see locally, but it's consistent with the idea that there is a rapid growth. The little red dots was talked about extensively. These are broad H-alpha emitters that are detected in spectroscopy and slitless spectroscopy, as shown here from paper by Yorick Mate. We know that many of these objects do have a host AGN, but their energy distribution is really puzzling. They have a red optical spectrum, rest frame optical, but they have a steep UV continuum. It's quite possible that not all of these are AGN. The MIRI data does not necessarily convincingly show the dust content from these objects. This particular spectrum is exciting, I think, because it's gravitationally lensed. And it's very difficult even to see the host galaxy in this image, which is possibly very significant. So using the primer sample, we've done a census of these objects using this curious SED shape to find them, and they don't seem to exist below a redshift of 4, which is intriguing. And one possible explanation is the dust is concentrated in the central regions of the galaxy, and as the galaxy expands and grows, then of course this color signature from the integrated light is no longer effective. But the luminosity function, it's very clear that there are more of these objects than we had imagined. And also, even if only a fraction of them are AGN, there are more subluminous AGN in the reionization era than we imagined. There are been claims of AGN at very high redshift. I'll just focus on one example. This is an X-ray image of a cluster that's been studied extensively with James Webb. There's this 4 sigma X-ray blip that is coincident with a galaxy at a redshift of 10.3. Is this a coincidence, or is this lensed X-ray emission from this galaxy at a redshift of 10.3? There's no evidence of any AGN activity in the spectrum of this object, so the jury is still out on this object. If this is verified from the bolometric luminosity that would be implied, if it really is beyond a redshift of 10, this would be truly remarkable, because it would just not be possible to create a black hole of this mass from stellar seeds. Let me wrap up with chemical evolution. So this is, I think it's just a beautiful spectrum. When I remember how hard we tried with ground-based telescopes to get any spectra at these intermediate redshifts and high redshifts, my message to the young people who are working in this area now, you lucky, lucky people. This is just fabulous data. And so we're now able to measure metallicities of these objects, gas phase metallicities, and we can see more or less in, next slide. Whoops, wrong way. One more. Well, yeah, it's really difficult. Chemical evolution. Now, how do we measure chemistry? Well, of course, there's still a lot of debate. We generally have used strong line ratios, but we know that the conditions at high redshift, the temperatures and the densities of the gas will likely be different. I like this trend from Robert Sporsani's stats again, because this is calibrated with this auroral line that's so-called collisionally excited line of oxygen, which has been tracked by Ryan Sanders and his team over a wide range of redshift. So we see, as expected, the decline in metallicity, down to a few percent of solar or so. So I want to end with cosmic dawn. Why is cosmic dawn so fascinating? It is the holy grail. You can read about it in the HST and Beyond report. Will we be able to recognize a first-generation galaxy free from chemical pollution? And of course, this is the birth of everything we see around us. So in some ways, it is a milestone. So simulations such as this one here, and there are many others by Harley Katz and collaborators, shows that there is a real problem, and that is, massive stars go supernova, POP3 supernova, very quickly in a space of only 5 million years or so. So the time window for seeing this pristine population is very, very short. Moreover, as we've heard in the meeting, POP3 and POP2 can intermingle within a single halo. So finding a POP3 signature doesn't necessarily mean that there aren't POP2 stars present in that galaxy. There are 2 interesting and intriguing claims for POP3 in the literature from early James Webb data. Maialino and his team find this line of helium. This has long been thought since Daniel Scherer's pioneering work, that this line is a marker of POP3 signatures, particularly if you don't see metal lines. And Eros van Zelle has this intriguingly highly magnified factor of 100 arc that's sitting across the critical line in a cluster seen at a redshift of 6 or so. This galaxy has been studied with the IFU, and the absence of O3 plays a very stringent constraint on the composition, less than 0.3% solar. So if I look at these objects in the context of Harley-Cat simulations, see if I can get that up, we can wrap up. If I place these on this on a diagram, the proof of burden of proof of POP3 is very, very challenging. Certainly, the ratio of helium-2 to H-alpha is promising, but it decays away very, very quickly, helium-2. So that's a real challenge. You need very deep spectroscopy to eliminate oxygen-3, and so there's a lot more work that has to be done there. So ultimately, I think we're not going to wake up one day and say we found a POP3 galaxy. It's more likely to be a statistical result. And of course, one of the great benefits of the longevity of James Webb in orbit is its synergy with SKA. And SKA, of course, has the capability for looking for an independent measurement of the birth of Lyman alpha in the intergalactic medium by the resonance with 21 centimeter absorption seen against the microwave background. So I'm an optimist. I do believe that, we will have the capability to make progress, although it's been challenging. And I'm reminded, if I can just have one more slide, if I can just bring up my last slide. We have, we've looked over the years at, it's really amazing. Right. Experience has shown us that, I'm going to get these while the going is good. I'll see if I can get this up. Right. Yeah. There we go. Okay, so the Keck telescope, if you go and look at what the Keck telescope was going to do, go and read the book, the Blue Book in 1985. It was going to look to a redshift of 1. That's what the Keck telescope was going to do. And they got out to spectroscopy out to redshifts of 8. If you go and read Bob Williams's book about the Hubble Deep Field, there was real skepticism that there will be any galaxies beyond a redshift of 2. So, of course, the Hubble Deep Field reached to a redshift of 11 or so, and likewise the Spitzer. So, it's election day in Britain today, and so there's one thing you have to remember from this talk, and that is, unlike politicians, astronomers always deliver more than they predicted.
Thank you very much. Any question? Okay, Nabila.
Thanks a lot for this great presentation and for the fantastic closing words. I was wondering whether you could comment on our understanding of the dust at very high redshifts and how this entangles with the estimates or understanding of the high redshift galaxies.
Which
Dust. So could you comment on our understanding of dust at those high red?
Dust.
Yeah, dust.
Yes. Okay. So dust forms. I mean, people have tried to find dust in many of these galaxies with ALMA. It's very challenging. Dust is seen, readily out by ALMA to redshifts of 9 or so. We do expect dust to be formed very quickly. So the idea that dust, is blown out of early galaxies because of their radiation pressure is a sound one. I just don't think. I think it's probably a continuous process. It's not sufficient to explain the visibility of these galaxies beyond a redshift of 10. I think there's a tendency in astronomy to think when you have a puzzling result that there's only one explanation, and Team A comes up with explanation A, Team B comes up with explanation B, and so forth. And in my experience, it's usually a mix. And so I think, there's plenty of evidence that galaxies are bursting, and there's plenty of evidence that dust is getting less frequent as one goes to higher redshift, even though we imagine it's definitely being formed in the galaxies. Dust does form very quickly in star-forming regions.
There is up there.
Hi, Richard. Thank you for that comprehensive overview. It was great. I wondered if you wanted to comment on, you mentioned the overluminous galaxies that have been found by JWST, and I wondered if you wanted to comment on the stellar masses that have been inferred from there, and what sort of side of the fence are you falling on in terms of, is it IMF or something in our sort of assumptions of how galaxies form that's going on there?
Yeah, well, that's a very, I couldn't see you, where you are, but, you know, okay. Oh, yeah, right at the back. Okay. Yes, well, stellar masses are dependent on one important variable, and that is the past star formation history. And, you know, without the full wavelength range, that's very, very difficult. And so we've seen that if you take a spectral energy distribution, say, without MERAC, at high redshift, then you generally tend to estimate to underestimate the contribution of long-lived stars. And so those stellar masses, in some sense, could be underestimates, which is, of course, very interesting. I don't think that the stellar masses of the galaxies beyond redshift 10 are part of the problem. I think what we're finding is the star formation rates are already so high, that doesn't seem to agree with what we would have expected from the theoretical prediction at a constant star formation rate. So I imagine that, something that we all dread, and that's the mass function is skewed to higher masses at early times, is interesting and likely to be productive. And so that's why I threw in that little snippet, which I know people in the audience are working on, and that's the contribution of nebula continua, which reddens the light compared to the starlight. So if this can be fleshed out, it may be an additional contributor to the luminosities of these galaxies. So to summarize for the non-experts, I think we have bursting, we have dust-free systems, and then we have the logical possibility of supermassive stars, which is not a surprise. I mean, theorists have been saying that in these early periods when the gas clouds are pristine, they won't fragment in the same way as they do in the Milky Way. And so the mass function will likely be skewed to massive stars. And there's lots more evidence that I haven't had time to cover about the nitrogen excess in some of these galaxies. So it's an exciting time.
Okay. One last question. There, please.
Hi, thanks for the beautiful talk. So about the red dots, the little red dots, as much as I love AGN because I work with them, the way I understand it from what we heard today and the other days is that not all AGN at the high redshift look like little red dots.
That's right.
And not all little red dots might be AGN.
Right. I think that's a very accurate summary. But there are a lot of them, and we didn't know they were there before. That's the exciting. So as I said, progress and surprises. So, yeah. Okay.
Okay, thank you very much, Richard Ellis again.